Hello everyone. This week for the review, I think I'm going to go through the review in the book, probably most of the questions. Since this was a little bit longer and maybe more difficult chapter. So, yeah. So the review's on page 451. The first question, of course, is the vocabulary words. There are 5 vocabulary words on the test, so I would make sure that you know the laws of thermodynamics, that you know what change in enthalpy is, that you know what entropy is, and that you know what activation energy is. So consider that a little bit of a clue. I will also tell you on the test, you do not need to draw any Lewis structures. The Lewis structures that you need for bond energy will already be drawn for you. And I can't remember if you're going to need this or not, but know that 25 degrees Celsius is the same as 298 Kelvin. Okay, so no Lewis structures. And 5 vocab. Okay, so question number 1 was the vocab. So again, you're probably gonna wanna know A, D, F, G, and H. This was a hard chapter, so I give you that. Okay, question number 2. A reaction is determined to be spontaneous at 25 degrees Celsius. Does that mean it will automatically happen when you mix the reactants at 25 degrees Celsius? So it's telling you it's spontaneous. Will it automatically happen? The answer is no, okay? Because remember, even spontaneous reactions sometimes need a little help or a little bit more activation energy to get going. Okay? So they may need activation energy for a kickstart. Okay? Spontaneous just means that once the reaction is started, it will keep going by itself. Okay, so the classic example that we've been talking about in this chapter is a piece of paper burning. Actually, a piece of paper burning is considered a spontaneous reaction, okay? Because once I start it burning, it will keep burning. Okay, but it doesn't automatically happen. This paper isn't bursting into flames at 25 degrees Celsius, which is average room temperature. Okay, so the answer number 2 is no. Just because it's spontaneous doesn't mean it will automatically happen. Okay, question number 3. A reaction has a positive delta H. Is it endothermic or exothermic? Okay, I hope you know by this time that a positive is endothermic. Okay, a negative delta H, on the other hand, is exothermic. Okay, don't know, you're just gonna, if you don't have this figured out yet, you're gonna need to just get this straight in your mind somehow. Number 4, 2 reactions occur and each causes the beaker in which it is done to get hot. Okay, so I've got 2 beakers and I've got 2 reactions going. Say hi, Emmy. The first one gets much hotter than the second. So they're both hot, but one gets much hotter. The same number of moles of reactant are used in each. If the delta H's are negative 355 kilojoules per mole and negative 214 kilojoules per mole, which belongs to the first reaction. So which belongs to this first beaker. Okay, these are both negative, so they're both exothermic. And that makes sense because if it's exothermic, they're gonna get hot, but we were told that one gets hotter than the other. Well, this one, the negative 355, is giving off more energy. It's giving off 355 kilojoules of energy. Or you can even think of it as 355 kilojoules of heat per mole. So this one is going to get hotter than this second beaker because it's only giving off 214 kilojoules of energy or heat per mole. Okay, so the answer to number 4 is the first beaker, or the first reaction. Okay, number 5. Using the bond energies on page 420, determine the delta H of the following reaction. Okay, so the reaction is CH4 plus 3Cl2 yields CHCl3 plus 3HCl. Okay, and it's telling us to use the bond energies. Okay, now bond energies is the only equation in this whole chapter where it's reactants minus products. Okay, so we're going to take the bond energies of both reactants and subtract the bond energies of the products. Every other equation is the products minus reactants. So remember that bond energies is reactants minus product. Okay, so to use bond energies, this is where I need to know what the Lewis structures look like. Now again, you won't need to come up with the Lewis structures on your own on the test. On this question we did. So CH4 is going to end up looking like this. Because C has 4, the H each has 1 and it wants 2. Okay, and then I have 3 of these Cl2s, and each Cl is 7, has 7 electrons, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this is going to make a double bond. They're going to share both of their single bonds here, and that will make them have a valence electron of 8. Or I'm sorry, a valence shell of 8 electrons. Okay, but there's 3 of these, all right? So don't forget, we have 3 of these, right? 3 Cl2s. So here's my 3 Cl2s. And then that yields a CHCl3. So our C we're going to put in the middle. It has 4 electrons, 1 on each side. We'll plop our H up here. And now the H is happy. And then our 3 Cl's go around. And each of them has 7, so that means this is going to share a single bond. Okay, and then finally we have 3 HCl's. This one's pretty easy to come up with too, because again, chlorine has 7, so that's going to form a single bond with my hydrogen, but remember there are 3 of those. Okay. So with bond energies, I need to take all the bonds into account, okay? So it said look at the table on page 420. So I'm going to turn to page 420. Now, if you need any of these tables, they will be on your test, okay? So any values from these tables that you need will be at the top of the test. Okay, so I have 4, right here, I have 4 single bonds between hydrogen and carbon. All right, so I have 4 of those. Now I'm going to look at the table. Hydrogen and carbon is 410 kilojoules per mole. Okay, then I have double bond here, double bond here, double bond here. So I have 3 double bonds between 2 chlorine atoms. I finding this on my table? Oh, sorry, this isn't a double bond. This is a single bond. This is a single bond. I'm so sorry, guys. This is a single bond. Okay, so I have 3 single bonds between my chlorine. This is one problem with this being one-way communication, is you guys can't question what I'm doing. And those are 243 kilojoule per mole each. All right, then I'm moving to my products, so I'm going to start subtracting. Okay, I have 1 bond here between an H and a C. Okay, so I have 1 of those that I need to break, and we've already looked those up. That's 410 kilojoules per mole. And then on this same molecule, so we've done that one, on this same molecule I have 3 single bonds between carbon and chlorine. So again, I'm in reactants, so I'm going to subtract my 3 single bonds between carbon and chlorine, which are 330 kilojoule per mole. Then I should have written smaller, but lastly, I'm in my products, so I'm going to subtract. I have 3 single bonds between hydrogen and chlorine. And if I look that up, that's 432. Okay. So doing this all out, I end up with 4 times 410 is 1640. Okay, let's talk about these units for a minute. When we're multiplying by the 4, the 3, the 1, the 3, the 3, that's canceling out the mole. So this ends up being 1640 kilojoule plus 3 times 243 is 729 kilojoule. And now I have a minus 410 kilojoule. Another minus 3 times 330 is 990 kilojoule. And then minus my 3 times 332. I'm sorry, 3 times 432 is 1296. And if I do all that, 1, 2, 3, 4, 5, I just want to make sure I have everything. 1, 2, 3, 4, 5. We should end up with a delta H equal to negative 327. Okay, which if you look at significant figures is negative 330 kilojoule. Okay, so the nice part is on the test, this will be done for you. Okay, but don't forget to look at every single bond, especially if you're given a molecule like this, because this molecule, I had 1 single bond between H and C, and then I had 3 single bonds between carbon and chlorine. So here's my 1 single bond between carbon and hydrogen. Here's my 3 between carbon and chlorine. And then the only other thing to remember with these bond energies is we are taking reactants minus products. All the other equations are the products minus reactants. Okay. All right, let's look at number 6. Number 6 says, the change in enthalpy of the following reaction is negative 137 kilojoule. My book actually said kilojoule per mole, but the question should just be negative 137 kilojoule. So if the unit is wrong in your book, you can cross that out. And it wants to know what is the energy of the triple bond between carbon and nitrogen. So here's an example where it gives us the Lewis structure. All right, so I'm on number 6. Let me just write this down quickly. We have C, N, 1 in between. These are all H, N, This is an H and an H. Okay, and the question is, what is the bond energy of this right here? Okay, it tells us that delta H, or the change in enthalpy, is equal to negative 137 kilojoules. Okay, so again, we can use that table on page 420. Whenever we see these Lewis structures, we're going to use the bond energies. And again, because we're using that bond energy table, we're going to take our reactants minus our products. But in this case, we don't know one of our bonds, but that's okay because we know delta H. Usually we're solving for delta H, so our unknown has just changed. Okay, so we can say delta H is equal to all our reactants, or all the reactant bonds, minus all my product bonds. Okay, now let's start substituting some values in. We know that our change in enthalpy is negative 137 kilojoules. All right, now let's start plugging in our reactant bonds. We have one single bond between carbon and hydrogen. Okay, so we have one single bond between carbon and hydrogen, so that's 1 times 410. Okay, then this is our unknown. All right, so let's just put an X for that, for simplicity's sake. All right, we'll say this bond is our X. This is the one we don't know. There's only one of them, so that's all good. All right, and then we have 2 single bonds between hydrogen. So that's 2 times 436 kilojoules per mole. Okay, now I'm going to start subtracting the bonds in my product. Okay, so I have 3 single bonds between carbon and hydrogen. Okay, carbon hydrogen on my table is 410. I have 1 single bond here, and maybe it's